Hello and welcome to worksheet number 9. This one's on hashing. So hashing is a very big topic in this class. It's a very big topic in computer science in general. If you ever decide to go into anything like cryptography or more CS theory things, you will see hashing come up a lot. It's a very, very useful tool. It's very exciting that we get to teach it to you here for the first time. And this is also a personal favorite topic of many of the TAs in this course. This is really one of the most popular data structures applications that we do in this class. So it will be cool. So this one, though, we are focusing in this first problem mostly on external hashing, and then we're going to talk a little bit more about kind of hashing as a broader concept in the second question. So let's just run through this first problem. This is basically a mechanical problem that's going to test if you kind of understand how a hash set or a hash map or a hash table in general sorts things. Okay, so in this first question, consider we have an external chaining hash set below, doubles in size when the load factor reaches 1.5. Notice it's not when it exceeds 1.5, but when it reaches 1.5. And we assume we're using the default hash code for integers, which just returns the integer itself. Okay, so let's just take a quick look here. What is the load factor for this hash table that's written here? And it's 1. How do I know that? Because it's basically the number. So load factor is equal to number of elements divided by number of buckets, right? That's how you get the load factor. So in other words, the load factor is the average number of elements per bucket. And so another way you can see that the load factor is 1 here is we just have 1 element in every single bucket. Okay. So right, whenever this gets to 1.5, we're going to double the size of our hash table, which means whenever this gets to size 6, which as a spoiler is probably going to happen in this problem, because why else would we tell you? Anyways, so let's just go through the process and draw the external chaining hash set, the results if we insert 18. Okay, so I'm just going to use this hash table that is up here. So how do we insert something into a hash table? First, we take the hash code of the thing. So I'm going to represent that as basically just saying, step 1, take hash. And this is just going to mean we're taking the hash of 18. H is just, I'm using it to represent a hash function. Since an integer just returns itself as we've defined up here, that just means that we're going to get 18 because the integer returns itself, but this could be anything. It could be a string, it could be a dog object, it doesn't really matter. We get the hash. 2 is we mod hash by the number of buckets. And so here we see that there are 4 buckets. So we're going to take 18 mod 4, which is equal to 2, right? And then we are going to finally put elem at end of chain in the bucket. So what bucket? In bucket 2. So we go to 2 right here, and we're going to put 18 at the end of this chain. This is how we're going to represent it. Keep in mind, this is just a linked list. These nodes just represent linked list elements. So if it helps you to think of it, you can think of it as like an int list that has like a value and then it has an X pointer or something. We're just kind of abbreviating it a little bit here. Anyway, so that's the steps to putting anything into a hash table. You take the hash of the thing. So in this case, we took 18 and we got its hash, which was just 18. We mod the hash by the total number of buckets. Number of buckets is 4, 18 mod 4 is 2. And then we put the element at the end of the chain in that bucket. So that's why this ends up here. Okay. So then that's the first one. And then the second one is draw the hash set that results if we insert 5 after the insertion is done in part A. So we're going to keep this hash table here, and now we're going to insert 5. Okay, so there is actually an additional step here. Maybe you could call it a step 0, which is basically make sure you do not exceed the load factor. So basically, consider what would happen. If we put 5 into this hash table, right, it would go in here somewhere, and that means there would be a total of 6 elements in the hash table. If we do our little load factor calculation here, number of elements divided by number of buckets, 6 divided by 4 is 1.5. And every time the load factor reaches 1.5, we're going to double the size of our hash table, right? So before I even put the element 5 in, I know I already need to double the size of the hash table. Okay, so let's do that. Let's double it. This might be giving you some flashbacks back to project 1 where you had to double the size of an internal array in ArrayDeck, and it is really the same thing, right? It's just there are too many elements. This always looks terrible. Can I draw a straight line? That's close enough. There's too many elements, so we need to double the size of our data structure, and we need to resort all of the elements that are currently extant in the data structure into the new one, right? So we're going to create a new list. It's going to double in size, so 1, 2, 3, 4, 5, 6, 7, 8 divisions. So we have 0, 1, 8 is not the number after 1, 2, 3, 4, 5, 6, 7, 8. So here I have a new array. It's the same thing as the old array, it's just twice as big. Okay, so let's sort everything from the old hash map into the new hash map. Okay, so the first thing we're going to do is we're going to take 8. We're going to take its hash code, which is just 8, right? And then we're going to mod it by the number of buckets, which is now 8. It's no longer 4. So 8 mod 8 is going to be 0, which means 8 is going to end up in bucket 0. Same place it was before, but this won't always be the case. So now let's sort 25. 25 mod 8 is what? 1. So it's still going to end up here. And then same thing for the next two. 10 mod 8 is going to be 2, so it ends up in bucket 2. 18 mod 8 is 2, so it ends up in bucket 2. And then let's sort 15. Okay, what is 15 mod 8? 15 mod 8 is 7, so it's going to end up in bucket 7. Okay, this is the important thing to note. This is the reason you can't just copy paste the locations of all of the elements as they existed in the previous internal list to the new one, because sometimes something mod, twice the number it was before is not the same thing, right? Notice how 15 ended up in a different bucket. Another way you can think of it is that if we always just kind of copy pasted everything into here and then only added new indices afterwards, eventually this area would probably get pretty full, and then the area below would not get very full over time. And that's something we want to avoid in hash tables. We want to make it so that things are generally pretty equally spaced out the whole time in the hash table. That's how we get our best runtime. Okay, so now we've sorted everything from the old hash table into the new hash table. That means the only thing that is left for us to do is to actually insert 5, which was the original thing we were trying to do before we did all of this resizing stuff, into our new hash table. How do we do that? Well, we take the hash code of 5, which is just 5. We mod it by 8, which is just 5, which means that we're going to put it in index 5, just like this right here. And that's how you do all of this. Now, if we check what the load factor is, right? The load factor is there are 6 things in the hash table. How many buckets are there? There are 8. It is now a comfortable 0.75. It is below the 1.5 that we had before. So we can add a bunch more elements into the hash table without resizing. But once we hit that 1.5, we'd resize up again and again and again. Okay, I hope that makes sense. Those are some of the basic mechanics of how you're actually going to insert things into a hash table. And I hope this helps.